Welcome back, Calculus 2 students. Today we're going to look at the area under a curve that is described parametrically. So you may recall that in a previous video, when I was describing parametric curves, that I indicated that the textbook describes something called a cycloid, and then I didn't cover that myself, but I pointed within the screen capture video at the part of the textbook where that was discussed, encourage you to read it. So on the board I have such a curve, a cycloid, that's generated by a circle of radius 2. And so I encourage you to once again go back to the textbook, read where that comes from. But I put a piece of the graph that we need for our purposes today, so we'll just rely on this information. So we have x of t is given by 2 times t minus sine t, y of t is 2 times the quantity 1 minus cosine t, and the graph of that parametrically defined curve is going to be this sort of bouncing curve that stays above the x-axis. The question that we'd like to answer is, what is the area under that curve in one of these little segments? And so we're going to focus between the 0.00 and the 0.4 pi 0, which correspond to t equals 0 and t equal to 2 pi. And you can verify for yourself these 3 points by plugging in the t values. So if you plug in t equals 0, you can see how x is going to be 0, and then y is going to be 0 as well. If you plug in 2 pi, you can verify for yourself that you're going to get 2 pi in the parentheses, and therefore 4 pi for the x value, and you're going to get a 1 for the cosine value, and therefore a 0 for y, and likewise test out t equal pi for yourself. But the question remains, how are we going to get the area in there? And let's for the moment pretend that this curve is described as y equals f of x. If that was the case, we would just use your standard garden variety integral to do this. And so you'd have the integral from, let's say, x equal a to x equal b, f of x dx. In our case, since we know that the boundaries are defined by x equals 0 and x equals 4 pi, that's what we've used right here, 0 and 4 pi. But we'd have to have an appropriate expression for f of x and then also know how to integrate it. So let's keep it general here. Let's just say from a to b and see if we can understand the relationship between x, y, and t that will yield a formula that we can use to do the integral as needed. All right, so what is the integral of f of x dx? If we go back to our definitions, it's a limit as n goes to infinity of some kind of a special sum, a Riemann sum. And so if I'm integrating from a to b, then I'm going to have some, let's correct this, we're going to have some sigma here from I equal 1 to n that involves some particularly chosen xi values at which to evaluate the function, and then maybe some differences in xi. I'm going to use delta x. I'm going to refrain from doing the most general case and just look at regular partitions for the moment. But with it, if we partition into rectangles, then we can take the width of the rectangle as delta x, and we can pick inside of each one of those rectangles a particular x value to determine a height of a rectangle to use. So I don't want to rehash all of Calculus 1's discussion of where the integral comes from, but hopefully this looks familiar enough to you that we can proceed. So I don't want to get into limits. I'm not going to get into heavy proof here. I'm just going to focus on what these symbols are telling us. And if this curve is given by some function f, well, we know the height is given by the y value. And so we can replace this f of x I bar with a y value computed at the corresponding t bar, or ti star. So let's do the limit as n goes to infinity, I equals 1 to n, and where we see our f of x, that's going to be a y value that's computed at a particular t value that corresponds to the x value. Furthermore, this delta x, I'm going to rewrite it as a delta x over delta t, and then times a delta t, seeing how the delta t's would cancel and take me back to delta x. So without getting into the technical details, as we replace this sigma notation with the integral, applying the limit, it seems reasonable that this guy right here would be your y of t, the delta x over delta t, when you apply the limit, ought to turn out to be a derivative, x prime of t, and then of course your delta t becomes your dt. We need to know that we're going between two t values, and so what I'm going to do is point out that I'm using alpha and beta, where x of alpha is a and x of beta equals b. And so that this was an integral defined using x values. This is an integral defined using t values. So now that we've got this formula here, let's go ahead and copy that down. And I'll go ahead and emphasize this: t equal alpha, t equal beta, y of t, x prime of t, dt. And let's look how that setup appears for the particular function that we're exploring right now. And so the t values that are our limits of integration are 0 and 2 pi. The y of t is given to us as 2 times the quantity 1 minus cosine t. We need to compute x prime, and so x prime is going to be 2 times the derivative of t, which is 1, minus the derivative of sine t, which is cosine t, and then we need a dt. And so if we're just focused on the setup, we've got that so far, and in fact we can write this a little bit more nicely. 4 times 1 minus cosine t squared, and then we can talk in a moment, if necessary, how to finish this out. But you can algebraically expand this, right? So ignoring the 4 for a moment, 1 minus 2 cosine t plus cosine squared t. And those are all things that we learned how to integrate earlier in the semester with techniques of integration. And so that cosine squared requires an identity, the 1/2 times the quantity 1 plus cosine 2t. So I'm going to leave that unfinished for now. But before I finish this topic, I want to come back and revisit this guy right here. I want to remind you that earlier in the semester when we discussed trig substitution, we talked about how it was a reverse substitution. And so when we talked about trig substitution, you might have something like x equals 3 sine theta, where you're contrary to our common sense that may dictate to us, we're trying to take a problem without trigonometry and purposefully put trig into it. And so in the process, we might discover somehow that we needed a substitution that looked like this, and then we compute dx equal 3 cosine theta d theta. And I want to point out how this guy right here, being the derivative up here, that's like x prime of theta and then d theta. And so we've actually done this process before that we're repeating now. We just didn't discuss it as if it was a parametric approach. It was trig substitution. It had its own names and own vocabulary. And so this right here is actually a kind of a repeat of something we've seen before, the idea that dx ought to equal x prime t dt. It's another kind of reverse substitution. Okay, so that's it for now for this directions for computing area under a curve, or any other integral for that matter, that's an integration of y with respect to x. You could just use y of t, so you're using your y value, but the x prime t dt takes the place of dx. Just make sure that you use t values and not x values before you integrate. I would encourage you guys to go ahead and finish this and see what answer you get, and you could let me know in the forum whether you get stuck, or maybe you could share your answers with each other and see if all of you get the same thing. All right, on to the next topic.